Powerful robots are not working closely with humans and are often kept behind fences since they are too dangerous. The common approach to bridge this gap is to use a force-torque sensor on the end effector to detect the intended motion. However, when co-manipulating objects in 6 degrees of freedom, it is hard to disambiguate force and torque, especially when the object is elongated. How can we make powerful robots co-manipulate objects with us, in 6 DoF, while being amenable to our instantaneous needs, all without a force-torque sensor? We believe the answer is adapted compliance. Making the robot more compliant when it is unsure of the human intention and stiffer when it is competent allows the robot to transition between a leader and a follower adaptively. In order to achieve this, 3 problems need to be addressed. How to represent human intention and how do we estimate it? Knowing the intention, how should the robot adapt between being the leader and the follower? How do we make sure the robot remains passive, stable, and away from infeasibilities? Our method solves these problems with the control diagram shown here. For intention estimation, we choose a simple representation that can be estimated in real time using 2 particle filters. More specifically, we assume the human intent can be represented as a simple goal-oriented dynamical system, or an attractor that describes where the object is going and a dynamics matrix describing how the object is going there, generating a reference velocity in both Cartesian and rotational dimensions. In fact, dynamical systems, or DS, has been widely used for controlling manipulators, ensuring stability and compliance around a trajectory without replanning. However, works that use this method usually assume predefined nominal DS, or learning DS from a few demonstrations. Instead, we use particle filters to estimate the parameters of the DS, highlighted in yellow, in real time. With the robot being adaptively compliant, we can get away with using past velocities as observations without a force-torque sensor. Using the estimated intent, we use competence-based variable impedance control to dynamically adjust who is the leader. Given the reference velocity predicted by particle filter in the previous step, and the velocity tracking error here, we compute competence as shown here, so the higher tracking error, the lower the competence. We then compute task space force and torque with a variable impedance controller and vary the gains with the competence, achieving roll adaptation on a continuum. As a result, if the human pushes on the robot, increasing the tracking error, the robot will be less competent and use less control effort, leaving the 6 DoF movement up to the human and doing only gravity compensation. Lastly, to satisfy both human and robot constraints, we ensure goal pose feasibility in the particle filter and joint space feasibility in the capability-aware controller. In the particle filter, we implement a particle trimming scheme to remove goals that are infeasible for the robot based on inverse kinematics. On the other hand, we shape the particle filter noise with human manipulability ellipsoid as an indicator of human capability and comfort, demonstrated by the white dots here. The capability-aware controller converts task space output to joint torques, and additionally track a preferred configuration as the null space task and enforce joint limits constraints. Putting it all together, we created a system that adaptively helps human with the estimated intent, while satisfying constraints. We show in the paper that our method is passive under mild assumptions and is closed-loop stable. To evaluate our method, we design a game where the subject is asked to move a 5 kg object towards the goal pose unknown to the robot. We use a force-torque sensor on the handle to record the user effort as integrated force and torque over time. With 20 such trials from 3 subjects, we find our method saves 17% force and 23% torque, compared to a well-tuned admittance controller using a force-torque sensor. We also find that our method performs similarly to adaptation method, which knows the ground truth goal pose, and selects between goals using human force measurements. Please use the QR code to get more information. We have integrated this work with an LLM that you don't have to yell at your robot, if physical corrections are allowed as the communication interface.